In this lesson, we're going to be continuing our look at trigonometry. Specifically, we've moved on to trigonometry where we use radian measure as opposed to degree measure for angles. Quick reminder or refresher, one of the things we'll be making use of are the primary trigonometric ratios, so sine, cosine, and tangent. So this is a quick and easy way to remember how to come up with those ratios. SOHCAHTOA is a mnemonic, and it depends on the location of the adjacent side, the opposite side, and the hypotenuse. This is review from at least a couple of years ago. So if you need to spend any more time on that, you should go seek the appropriate resources. And another thing, another piece of review, which is the special triangles. Here I've modified the special triangles from degrees into radians, but we use these to come up with exact values for certain trigonometric ratios. For example, if I wanted to know the sine of pi by 3, I would look here. Here's pi by 3, and I want sine, which is opposite. So there's the opposite side over hypotenuse. Here's the hypotenuse. And so the sine of pi by 3 has the exact value of root 3 over 2. Some people take this one step further and they actually just memorize all of these. I don't actually recommend you do that. It's really a good idea for you to memorize these special triangles though. If you can construct these special triangles from memory, then you can quickly and easily come up with all of these trigonometric ratios. Next thing, and now into the, we're still this, I would still say this is really review in the sense that this is something you would have looked at previously, but some terminology that we need to make sure that we remember. When we talk about an angle in standard position, that's an angle that is measured with respect to the positive x-axis, and we measure the angle in a counterclockwise direction. Or positive angles are measured in a counterclockwise direction. Negative angles would be measured in a clockwise direction. So that's what it means to be in standard position. This green line is known as the initial arm, and this red line is known as the terminal arm. So the angle between the initial arm to the terminal arm is going to be described as an angle in standard position. That's often called our principal angle. If I think of this in terms of a triangle, however, I can actually use this initial arm and this terminal arm, because wherever this terminal arm ends, I'm going to end up, I could put a point on the end of that terminal arm. And that point would be defined by the coordinates x and y. And based on those coordinates would be a certain distance away from the origin. So I could figure out that value r using this relationship, which is the equation for a circle, or you could also view this as the Pythagorean theorem. So we can make a relationship between x, y, and r and this angle theta, because if I take these three sides and I label them opposites, adjacent, and the r value, I can use sine theta equals opposite over hypotenuse. Sine theta equals opposite over hypotenuse. I end up with y over r. I end up with x over r for cos and y over x for tangent. Similarly, for the reciprocal trigonometric ratios, so sine becomes cosecant. 1 over sine is cosecant, 1 over cos is secant, 1 over tan is cotangent. So I can define all 6 of these trigonometric ratios in terms of the values x and y, or the coordinates of that point, and r, the length of the terminal arm. Another piece of review material is the idea of a related acute angle. The related acute angle is the positive acute angle between the nearest x-axis and the terminal arm. So you can see here I've given the example of theta, which is my principal angle, being 5 pi by 6. And this is how it's represented here. If I want to know the related acute angle that goes along with this, that's going to be this value between here and here. So this is my related acute angle. Sometimes you'll also see just RA for the related, they'll just call it the related angle. I like to say RAA because I like to emphasize the idea that this is an acute angle. So you can see, first of all, I chose it here because this negative part of the x-axis is the closest part of the x-axis to this angle. And a couple of other things to emphasize, obviously the idea that it's positive and the fact that it's acute. When we were working in degrees, that meant that 0 degrees was less than the related acute angle is less than 90 degrees. These are positive numbers between 0 and 90. In radians, that means that 0 radians is less than the related acute angle is less than pi over 2. So that's something to keep in mind when you're coming up with these. The related acute angle is always positive and it's always an acute angle. So in this case, if I want to find this related acute angle, the way that I'm going to do that is I have this angle 5 pi by 6. My closest angle, or my closest x-axis, is at the negative x-axis, which is pi. So the way that I do this is I actually imagine going all the way around to pi and then having to come back by the related acute angle. Now, that's the very strictly formal way of doing it. And so what this equation or what this diagram says is that if I go all the way to pi and then I come back by the related acute angle, I end up getting 5 pi by 6. But although that is technically correct, you might find that to be a bit of an awkward way of expressing this. Now let's just go ahead and finish this off. I want you to see that this does work. So if this type of logic works for you, then that's terrific. So I'm going to leave the pi over here. I'm going to bring this 5 pi over 6, which means it becomes negative 5 pi over 6. And that negative RAA goes to the right side and becomes just the RAA, or the related acute angle. So that results in, and if I just rearrange this, the related acute angle is equal to pi minus 5 pi by 6. So pi is the full from positive x-axis to the negative x-axis, and then I subtract 5 pi by 6 and I'm left with this small wedge, the angle in this small wedge. But either of these, you could start here and work it out, or you could go straight to here and work it out. Either of those is perfectly fine. And in this case, we end up with our related acute angle. If we do this, let's do this fully, just so you understand. We need a denominator of 6 here. And so this currently has a denominator of 1. And so to get a denominator of 6, I have to multiply top and bottom by 6. So this becomes 6 pi minus 5 pi. And 6 minus 5 pi is equal to pi, or 1 pi. So I end up with my related acute angle is equal to pi by 6. Another thing that we need to refresh our memories on is something called the cast rule. The cast rule allows us to work through the idea that our principal angle could be in any one of the 4 quadrants. And so for that reason, we need to consider what is the effect of being in each of these quadrants. So for example, if we are in the first quadrant, then I know that my x coordinate is positive and I know my y coordinate is positive. On the other hand, if I'm in the, and of course my r value, well, my r value is always positive because the radius is always positive no matter where I am. If, on the other hand, so if I move into the second quadrant, well, what can you tell me about the x and y coordinates over here in the second quadrant? Let's move this. Have this make a little bit more sense. So positive x, positive y, positive r. Over here, well, now I'm on the left side. This is going to be negative x. It's still positive y. It's still positive r. Once I'm down here, I have a negative x and a negative y, but still positive r. And then over here, I have a positive x, I have a negative y, and I have a positive r. And what that tells us, if we go through our different ratios, and again, this is review, this is something you've seen before. If we think of, for example, let's just focus on sine. Well, let's for this quadrant, what is the sine of theta? The definition of sine is y over r. So over here in the first quadrant, what is sine going to be? Y over r is going to be positive. So sine of theta is going to be positive. Here in the second quadrant, y over r, that's positive over positive. So once again, we've got sine is positive. Down here in the third quadrant, sine is y over r. Y over r, that's going to be a negative over a positive. That's a negative. So sine is negative. And over here in the fourth quadrant, y over r, that's negative over a positive. That's telling me that sine is negative. And so we have sine is positive, sine is positive, sine is negative, sine is negative. And if we went and did this for all of the primary trig ratios, we would find, let's take all of this clutter out, what we would find is that all of them are positive in the first quadrant. So that means we have positive sine, we have positive cos, and we have positive tangent. If we went to the second quadrant, we would find we have positive sine, but we have negative cos and negative tangent. So the cast rule tells us that only sine is positive here. So the t being here, that tells us that only tangent is positive. So we're going to have negative sine, negative cos, positive tangent. And the c here tells us that we're going to have negative sine, positive cos, and negative tan. So the cosine's positive. So that's what the cast rule tells us. We can use the cast rule along with the related acute angle to solve for the angle in our trigonometric ratios or equations. So let's take a look at that and see what that's going to look like. So this says to evaluate using Cartesian definitions and special triangles. So Cartesian definitions, that means the x, y, and r definitions, but it also means, and I'm just going to remind you over here, this could be 0 or 2 pi. That's pi by 2. That's pi. That's 3 pi by 2. So you need to get used to those angles. That used to be your 0, 90 degrees, 180 degrees, 270 degrees. Then special triangles. 1, 2, root 3, pi by 6, pi by 3, 1, 1, root 2, pi by 4, pi by 4. And it's very useful to just have these things memorized. You don't have to necessarily write them down every time, although I think that's a good idea too. So let's do part A here. We want the sine of pi by 2. And the Cartesian definition, what I want you to recall for this one is I want you to recall the definition, which is that sine theta, what's the definition of sine? It's y over r. So sine theta equals y over r. That means it is the y coordinate over the r value, over the radius. So what we normally do when we're talking about this one, which is pi by 2, that means it's on, in this case, it's on the y-axis. So what we normally want to do at this point is remember these as coordinates. And these are coordinates on what's known as the unit circle, which means we're going to have a radius of 1 for all of these distances. So what are the coordinates of this point that is 1 unit away from the origin? Well, that would have an x coordinate of 1 and a y coordinate of 0. This one is 1 unit away, which means has an x coordinate of 0 and a y coordinate of 1. Here we have an x coordinate of -1 and a y coordinate of 0. Here we have an x coordinate of 0 and a y coordinate of -1. And so, in this case, we want to know the sine of pi by 2. And so what that is saying is the sine of pi by 2 is equal to the y coordinate divided by the r value. But the r value in this case is equal to 1. So in this case, it's going to be the y coordinate, which is 1, divided by the r value, which is a distance of 1. And so, of course, that just is equal to 1. So let me just put that in there. That is the y coordinate, and that is the r value. And so we end up with this final answer. Now you see, I didn't even use special triangles for that one. I am going to use special triangles and the cast rule for this next one. This next one says the cosine of 5 pi by 4. Now the first thing we want to do is express this in terms of its related acute angle, or let's actually find what is the related acute angle that goes with 5 pi by 4. Obviously, the better you are with fractions here, the better off you're going to be. When I look at this, the first thing I see is that, well, 5 pi by 4 is a little bit more than 4 pi by 4. And why do I care about 4 pi by 4? Because 4 over 4 is 1, so that would be pi. So 5 pi by 4 is actually this angle. 5 pi by 4. It's past the horizontal. Again, that's 180 degrees, which is now pi. So 5 pi by 4 is past that, but you have to make sure that it's not past 3 pi by 2. If we put that in terms of the denominator 4, that would be equal to 6 pi over 4. That's another way to think about this, which is pi by 4, or sorry, pi is the same as 4 pi by 4. So 5 pi by 4 is obviously between 4 pi by 4 and 6 pi by 4. I would hope that you can get to the point where you don't need to do this, but if you do need to do this, put these into common denominators with your principal angle, well, that's fine. It doesn't take that long, and it's definitely worth it. That means my related acute angle is right here. And if this one is 5 pi by 4 and it's just past 4 pi by 4, in that case my related acute angle is equal to pi by 4. So that's the first thing we do in that case, is we have to figure out what's the related acute angle. But the next thing we have to figure out is, if we express it in terms of that related acute angle, we have to take into consideration the cast rule. Because we're about to write this equals, oh, that's not what I wanted. So we're about to write this in terms of the cosine of, but we want to write this in terms of the cosine of pi by 4, which is the related acute angle. So the other thing we need to change here is, the other thing we need to concern ourselves with is whether or not we have to change the sign. So cosine is positive in the fourth quadrant, and first quadrant and fourth quadrant. It is negative in the second and third quadrant. So when I write this in terms of the related acute angle, because the cosine of pi by 4 is going to be positive, but the cast rule tells me that the cosine of 5 pi by 4 is going to be negative, I have to make that change in sign in front to account for the fact that I've converted from the obtuse angle to the acute angle. So this part comes from the cast rule, and this part is my related acute angle. And now I keep that negative in front, but now I look, well, what's the cosine of pi by 4? Cosine of pi by 4 is adjacent over hypotenuse from this special triangle. Adjacent over hypotenuse is 1 over root 2. And so I would probably finish off by writing this as negative 1 over root 2. Now, we've got this next example is going the other direction. It wants us to solve for tan theta equals this number, and it wants us to do that for any angle between 0 and 2 pi. So in order to do that, again, we're going to make use of the cast rule. In this case, unfortunately, we're not going to be able to use our special triangles. And the reason I know that is when I look at this ratio, forgetting about the negative sign, when I look at this ratio, I can see that 7 over 24 is not a fraction that I get from any of my special triangles. So I'm just going to have to use my calculator to do this one. When you're doing these calculations on your calculator, remember to switch over to Radian mode on your calculator. Okay, you've been doing everything in degree mode for a long time, but we're now switching over to Radian mode. So the way that I'm going to do this, the first thing I need to do is I have to figure out what quadrant am I going to be in. So I'm going to use my cast rule. And I can see here I've got tan is negative. So where is tan negative? Tangent is negative in these two quadrants. So that tells me that my answers are going to be in quadrant 2 or quadrant 4. Those are my two possible answers from this. So then the next thing I'll do is I will actually find, I will solve for a related acute angle. And what that means, I'm not going to find, sorry, I am going to find what the related acute angle is, but the way I'm going to do it is I'm going to say the tangent of the related acute angle is equal to 7 over 24. So you see, I've gotten rid of the negative sign, and I'm just going to find out what the related acute angle is from this. So that's equal to the inverse tangent of 7 over 24. And that is equal to, again, making sure that my calculator is in Radian mode, which it is. So I'm going to take the inverse tangent of bracket 7 divided by 24, close bracket, equals, and I end up with this unfortunate answer, 0. And I say unfortunate because it's not going to be exact, 0.2838. I'm going to go to 4 decimal places, 0.2838, and there are no units to go with that, but you could say radians if you wanted to. That would be fine. And then my last step is going to be for quadrant 2 and quadrant 4, what are my answers actually going to be? So quadrant 2 and quadrant 4. So in quadrant 2, what does that look like? In quadrant 2, that means my angle is over here, and my related acute angle is 0.2838. So there would be my related acute angle, and that would be my value theta. So how do I combine this with this? Well, over here the negative x-axis is the angle pi, and so again, if you do this literally, you could say that theta plus the related acute angle equals pi. But we're interested in theta, And you could go straight to this, which is theta must then be pi minus the related acute angle. So theta is approximately equal to, and I'm just going to go ahead and do that whole thing on my calculator. So I'm just going to say pi minus my previous answer, and I end up with approximately 2.8578. And again, you could say that has an angle that's units of radians, but it's not necessary. In quadrant 4 means I'm down here. So there is my principal angle theta, and that means my related acute angle is here. And in this case, we've talked about the fact that we start here on the positive x-axis, but if we go all the way around, that's the same as having gone around to 2 pi. So in this case, theta plus the related acute angle is equal to 2 pi. Or theta is equal to 2 pi minus the related acute angle. So I end up with theta is approximately equal to, let's see, 5.9994. 5.9994. I'm just going to double check that one. 2 pi minus 0.2838 equals 5.9994. Yes. And so those are my two possible values for theta. And another way, if you wanted to check this, I could take the tangent of theta. Remember, it was negative 7 over 24. So my left side is equal to tan of 2.8578 approximately, which is approximately equal to tan of tan of 2.8578 is approximately equal to negative 0.2917. And my right side is equal to negative 7 over 24, which is, and again, I'm going to just give an approximate value for this. So 7 divided by 24, that's approximately equal to negative 0.2917. Now these are not exactly the same because I've rounded, but it's a pretty good confirmation that what I've done here is correct. And I believe that's it for this lesson, and it is. It was a longer lesson, but it was mostly review material. The big thing that you need to bring forward from your previous studies is how to use the related acute angle in conjunction with the cast rule. The only real difference here from previous courses you've done is that we're working in radians instead of degrees now.